All right, follow up on why there are 6 hydrogen on E. Or come back to our graph. Why I count 3 hydrogens and I need to count this one, okay? Something that you haven't learned, but very soon you will learn in discussion. It's called chemical equivalence. Here and here, if we make a model, a very ugly model, but just like the carbon I'm pointing my finger with, okay, has a red hydrogen. Okay, that's the red hydrogen. You don't need to care about. Just trying to say this is the tertiary. There's another carbon bond out. Okay. Okay, but this 2, 1 and 2 is the other blue. Let me take the red hydrogen out just for a moment. There's something called chemical equivalence. That's if I free rotate this sigma bond, the bond between secondary and tertiary. This 2 green bond will change their place. Can people see? If sigma bond, if they do the free rotation, which means the chemical environments of carbon number 1 and carbon number 2. In this case, carbon number 1 and carbon number 2 are the same. So if they rapidly change their place, we will not be able to tell the difference between carbon number 1 and carbon number 2. When does this apply to? You see there's symmetrical plane. Okay, do this one works? No, it doesn't, because if you spin this part, here and here, they're in different chemical environments. This, let's say the secondary carbon B is closer to your tertiary. The secondary carbon C is closer to your tertiary. So they are in different chemical environments. So this only apply when you see symmetrical, and they are symmetrical if they rotate too much, like fast enough. You basically cannot tell the difference between these 2 because they keep, rotating. They're take each other's place. Then 1, 2, 3, 4, 5, 6 will say these 6 hydrogen are chemical equivalents. Something you will learn in discussion 6 or 7, I think.